Hi guys, welcome back to Data Every Day. Today we're looking at a data set of lower back pain symptoms. You can see we have a number of features about muscles and bones and just a bunch of medical statistics. And at the end, we have this column called class ATT. And this says if a patient is exhibiting abnormal or normal symptoms in the back. So what we're going to try to do is predict the if a patient is experiencing abnormal or normal symptoms based on the other features. So let's go into it. I'm going to be using PyCaret today as a way to select a model. So what we'll do is we'll train a whole bunch of models using PyCaret, and then PyCaret will tell us what it thinks the best model is, and then we'll create our own version of that model and hopefully optimize it to get better performance than what PyCaret has suggested. So let's see. I'm just going to collapse this output. We don't really need to see that. I'll wait for it to finish. And then I will import these imports. We have NumPy and Pandas, which we're using just to work with the data. Seaborn and Matplotlib.pyplot for visualization. I'm going to compute a confusion matrix and display it using Seaborn. And then standard scalar and train test split function from sklearn for pre-processing. Then we're going to import pycaret.classification, since this is a classification task. And we're going to get the confusion matrix and classification report from sklearn.metrics to evaluate the model's performance afterwards. Now the actual model that we're going to use as our main model, we're not going to import yet because we don't know which one we need. PyCaret will give us the answer to that, and then we'll import that later. Alright, so this is finished. This is finished. Now let's load in the data. So data equals, we're going to use pandas.readcsv to grab a CSV file. Here's the file path. So I'm going to paste that in there, take a look. And you can see we have, it's interesting, it looks like we have 14 columns. Interesting, it's showing all the rows. Let's do data.head so we don't have to see everything. It's just the first 5 columns. You can see we have this unnamed 13 column at the end, so this is an unnecessary column. I'm not sure why it's on there. If we look over here, it only says there's 13 columns, but over here there's 14. 1 through 12, 13, 14. Okay, so let's get some information on the data set. So we have 14 columns, and you can see everything except this last column has no null values because there's 310 total entries and 310 non-nulls in each column. So let's start cleaning the data a little. So first thing I want to do is just drop this column. It's unnecessary, not giving us any information. So data equals data.drop unnamed 13, dropping from axis 1. And then I also want to encode this class ATT. Let me show 10 examples, it'd be nicer. So this column, this is our label column, will either have a value of abnormal or normal. Right? If we look at that, class ATT dot unique, we want to see the unique values. You can see we have 2 unique values, but right now in its current form we can't feed it into the model because it's written as a text label. So let's just convert it to a numerical label. So the way I'll do that is I'll take the column and apply a lambda function to it. It takes in some x. X will be a given value of either abnormal or normal. And for each value, x will become 1 if x equals abnormal, and otherwise 0. So we'll then essentially take this column of abnormals and normals and turn it into a column of 1s and 0s. Where 1 means abnormal and 0 means normal. So we'll apply that. You can see here it goes. There's different values. I'm just going to overwrite the column. And now let's take a look at the data. We already dropped this. Let me just put this up here. And then take a look. Okay. I don't like that this scroll wheel, I don't want to be able to see all the columns, so I'm going to go into the console and type pandas.setOption max rows to 20. Now it only displays 20 rows at most. This actually looks like it's displaying 10 rows, but this is what I want in any case. Okay, so now that we have our data, let's split and scale it. This is just a one last step of pre-processing. This is a very clean data set. Obviously, there's no encoding I need to do here. Each column is numerical. The only thing left to do is scale the data and split it into a train and test set. So we'll scale the data. So I'm going to create a new scalar. This will be a standard scalar from sklearn. Standard scalar, sorry, not x. Standard scalar will give each column mean 0 and variance 1, so that most of the values for each column lie between -1 and 1. It just makes it nicer for our model to take in the data. So what I'm going to do is data.loc to take a slice of the data frame, and I'm targeting all rows, but column 1 through column 12. So what that's saying is just the slice of the data frame that contains these columns. So everything except the class at column. And because I want to scale this, I don't want to scale the class att column because those are our labels and we don't want to mess with them. But everything else we want to scale so that the relationships between the data points stay the same, but that the scale that they're on is smaller and more uniform. So we're going to set this equal to scalar.fitTransform itself. So the scalar is going to be fit to the data, and then it's going to transform each column according to the fit. Okay, and then if we take a look at the data after that, you can see that has happened. These -28, 15 values are gone. Now everything has values very close to 0, and they have equal means and variances across all columns. So now let's split into train and test sets. So I'm going to use data train, data test. So I'm splitting into train and test sets before I split the column off. That's just because the way PyChar takes input, it's better if it's in one data frame. So I'm passing in data, going to split it into train and test, and I specify a train size of 70% and a random state. This can be any numbers just so that we can reproduce our results. How about 200? Okay, now data train should be 70% of the data, 217 rows, and data test is 93, so the other 30%. Okay, now let's begin model selection. We could also, I wonder, how about we do a little visualization? I just want to see the correlations between the variables. So, how we'll say this, visualizing correlations. So I'm going to make a correlation matrix that's going to come from data.core. That'll calculate the correlations between all the columns. And then I'm going to create a new matplotlib figure, the figure size 12 by 10. And I'm going to create a seaborne heat map of the correlation matrix, turning on annotations. I'm going to set the minimum value to -1, since that's the lowest value a correlation can take on. And then we'll keep the color map the same. This should be good. And we'll show it. Oh, actually, well, this is fine. I want to do it before I apply the scaling. So let's run from the run before, and then just take a look. Yeah, this is already installed, so just be 1 second while it. Here we go. Okay. So we can see we have some pretty strong correlations around the first few columns with each other. The last half of the features don't seem to have very high correlations with any of the other variables. There's nothing here that's like exceedingly high. I mean, the highest one I see is 0.81, but I wouldn't say that warrants any feature removal here. It still seems like it's good to keep all the data, especially since we have such a limited set of features. For class at, so this is interesting, to see the correlations between your target variable and the other variables, it looks like we have, this seems to have some strong correlation with column 6, and somewhat so for columns 1 through 4. and column 5. So something about these first 6 columns is very important. We can go back to look at this. Now, I don't know much about biology and about human anatomy, but it looks like these 6 statistics here are more important to predicting than the remaining statistics. Alright, so let's get back. I just wanted to see what that looked like. I don't think I have to go any further. Maybe I'll put a title on this though. Correlation heat map. Okay. And let's get back to scaling. So I'm now going to scale the data. Take a look. You can see it's scaled like it was before. Now we're splitting to train and test, and now we're into model selection. So here's where I'm going to use PyCaret. PyCaret.classification.setup. All we have to do is run this function on the data, and we can specify any number of transformations we want PyCaret to apply to the data, but I'm not going to do that since we already scaled it, and I don't want to include anything else. It's a very small data set. But we're just going to pass in the train set and a target. The target column is called class_at. And the setup function will just load PyCaret up. It says, following data types have been inferred automatically. If they are correct, press enter to continue or type quit otherwise. So this is correct. They're all numeric, and that's our label column. So I'll press enter. And now it has finished setting up. You can see it has a whole bunch of options. These are just the default options. I didn't specify anything else, but you can normalize the data, transform it in any way, apply some PCA, ignore low variance. Yeah, you can do all sort of like filtering on the features and so on. But I'm just leaving it the way it is, and I'm going to now call PyCaret.classification.compareModels, and this will take a whole bunch of models and fit the models to our data, and then it will find the best model and return that. So I'm going to store the best model in best model. Alright, so I ran the compare models function, and we have a ranking of all the different models and their performances on the dataset. So you can see that logistic regression comes in first with an accuracy of 82.88 and an AUC of 0.893. So fairly good. Let's see what happens when we, because we stored the best model in best model. Let's find how the model performs on our test set. So to do that, we're going to have to actually split our data. So what I'm going to do is, because right now we have data train and data test, but I want it in terms of x and y. So what I'll do is get, we'll do y train equals data train sub class_at. So just that column dot copy, and x train is going to be data train dot drop class_at from axis 1 dot copy, and then we're gonna just copy that, paste it in, change this to test, and change this to test. Now we have split our data into x and y, although the train test split has remained the same. So now we can score our model on the test set, x test, y test. And we end up with an accuracy of 82.7%, which is just about the same as this. But let's see if we can do better using a custom model. So this uses logistic regression. So now I'm going to import from sklearn.linear model. I'm not just going to use logistic regression, but I'm going to use logistic regression CV. And this employs cross-validation and hyperparameter optimization to give us hopefully a performance boost. So now I'm going to create our own model. This will be our custom model called which will be an instance of logistic regression CV. And we're going to fit the model on the train set. So x train, y train. Alright, and then we will score that model on the test set and compare the results. So you can see that this model had it found the best hyperparameters to use, and we end up with an accuracy of 88%, which is far better than our 82.7. So it looks like using the information that PyCaret gave us, we were able to take that and refine it to get a even better result. So now, let's just get a few more. Let's get a confusion matrix for these results. So now I'm going to get the true y values. That'll just be a NumPy array of y test. We already have that data. And then I want to get the predicted values. This I can just get from model.predict xtest. So these will be the predictions for the labels, and these are the actual labels. Then we can get a confusion matrix. This is the sklearn.metrics.confusion matrix that I imported earlier. Pass in y true and y pred. And we can plot it in a new matplotlib figure. Figure size, this can be small, how about 4x4? And then I'm going to plot, we'll use a seaborn heat map here, sns.heatmap. Pass in cm for confusion matrix, turn on annotations. I'm going to include this format argument so that we see the counts as integers. Change the minimum value to 0, turn off the color bar, and I'll also put some axis labels on it. So x label will be predicted values, and plot.y label will be actual values, and the title will be confusion matrix. Alright, and here's our confusion matrix. You can see, even though we have a small number of examples, it has done very well. These are the true negatives, true positives. This is our false negatives and false positives over here. And you can see that we have very few false negatives and false positives. So let's also just get a classification report to get some more information about the confusion matrix. This is also from sklearn. We just passed in y true, y pred. And you can see our precision and recall scores are very high in both classes, and our F1 score, which is a combination of the two, is very nice as well. So it looks like our model is doing pretty well, and it definitely beat the one that PyCaret got for us. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe, hit the bell, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.